Okay, so in this lesson we're going to be talking about higher derivatives. So we're going to take the work that we've already done on derivatives and just extend it a little bit here. So first off, what are higher derivatives? How do we find them? How can we use higher derivatives, particularly of polynomial functions, to solve problems? Again, involving speed, velocity, and acceleration. So similar to the problems that we were working on in the last lesson. And then we're going to talk towards the end about sketching graphs of functions and their derivatives. And we'll do a little bit of work specifically relating to speed, graphs of speed and velocity and acceleration. So first off, what exactly do we mean by a higher derivative? Well, the derivatives that we've been talking about up until now have been the first derivative of a function. If we want to talk about a higher derivative, we might start talking about the second derivative of a function. And the second derivative of a function is the derivative of the first derivative, or the derivative of the original function. So we start with our function, f at x, and we can find f primed at x. This is the first derivative. If we then take that function that we got as our first derivative and take the derivative of that, we get the second derivative, f double primed at x. Or we could use a slightly different notation here. If we've indicated our original function by y, we can indicate our first derivative as dy dx. Then our second derivative would be d squared y dx squared. And sometimes you'll also see this notation. We start with a function y. Our first derivative is y primed. Our second derivative would be y double primed. Of course, you don't have to stop there. You can take the derivative of the derivative of the derivative, which would give you f triple primed, and so on and so on and so on. So you can keep taking derivatives as long as you still have a valid function to take the derivative of. So let's look at an example here, just to make this a little bit more concrete. I've got a function here, y equals 6x to the power 4 minus 3x squared plus 7x minus 2. I can take the derivative of this function to get y primed. So this is a polynomial, so I'm just going to use that power rule, term by term by term. So if I bring down the 4 times 6 is 24, x cubed, subtracting 1 from that exponent. Bringing down the 2 in my next term, I'll get negative 6x. And then my third term, let's see, I've got 7x, so that's just going to be plus 7. And of course, the negative 2 goes away because it's a constant. Derivative of a constant is going to be 0. If I want to find the second derivative, well, I'm just treating this function y primed as my original function, and I'm doing the exact same thing. I'm going to bring down the 3 and do 3 times 24 to get 72, x to the power of 2. Derivative of negative 6x is just negative 6, and the 7 goes away. So my second derivative here is 72x squared minus 6. So it's nothing different than what we've been doing up until now. We're just taking the derivative of functions. So what does the second derivative mean? Well, let's take a look at the kind of problem that we looked at yesterday, but then we'll start bringing these higher derivatives into it. So once again, we've got the position function for an object. It's given by this function, s at t equals t cubed minus 12t plus 36. And I've given ourselves sort of restrictions on our time here. This function only works for t between 0 and 10. Find the velocity and the acceleration at t equals 4. Well, we know how to find the velocity. How do we find the velocity? We're going to take the first derivative of our position function. So our velocity function is going to be 3t squared minus 12. And if we want to evaluate this at 4, we just sub in 4. So that's going to be 16 times 3 minus 12 gives us 36 meters per second. And we took the derivative of our position function because we knew that velocity was the rate of change of position with respect to time. Well, next up we want to find acceleration. What is acceleration? Well, acceleration is how our velocity is changing. It's the rate of change of velocity. So to get our velocity function, a is a function of t, we are going to take the derivative of our velocity function, or the second derivative of our position function. So going back to our velocity function is 3t squared minus 12. The derivative of that is going to be 6t. Okay, that negative 12 goes away because it's a constant. So now, if we want to find our acceleration at time 4, it's just going to be 6 times 4, which is 24. What are the units going to be here? Riley? Meters per second squared. So our position function has units of meters. Velocity has meters per second. We take another derivative, we get meters per second squared. Okay, next part of our question here. When is the object's velocity increasing, and when is the object's velocity decreasing? Well, this is similar to what we did yesterday when we had our position function, and we asked when is the position increasing and when is the position decreasing. We said position was increasing if it was moving to the right, position was decreasing if it was moving to the left. And we were able to check that by looking at whether our velocity was positive or negative. For velocity, we can do the same sort of thing by looking at the sign of our acceleration. So velocity increases if our acceleration is positive, and our velocity decreases if our acceleration is less than 0, so if it's negative. So we need to use this acceleration function that we found in the previous part of this question. So I'll just say velocity going up, increasing, velocity going down, decreasing. When is our velocity increasing? For what values of t? Malcolm?
When t is greater than 0?
Yeah, for any t greater than 0. And then it's going to be decreasing for any value of t that is less than 0. T would have to be negative there. Okay. And if we wanted to, we could set this up as an equality. We could take this and we could say, 6t less than 0, divide both sides by 6, and get t less than 0. But strictly speaking, because we placed that restriction on our domain, we said that our function was only valid from t equals 0 up to t equals 10. We could make a little note here that says that this is not in the domain. So strictly speaking, our velocity is never decreasing. Now, here's the tricky question. when is our particle speeding up and when is it slowing down? And why is this question different from the previous question? So what is the difference between speed and velocity? Or what is the relationship between speed and velocity? How are these two concepts connected to one another?
Speed is just a scalar, just a magnitude, while velocity has
Absolutely. So speed is a scalar quantity. Velocity is a vector quantity. The way that we could express this mathematically is that speed is the magnitude or the absolute value of the velocity. Okay. So if our velocity is increasing, okay, our particle isn't necessarily speeding up. The velocity can be increasing. Let's say our velocity is -5. It can increase from -5 to -4 to -3. It's getting larger in terms of it's increasing. It's becoming less negative, but its magnitude is decreasing. So the particle would be slowing down even though its velocity is increasing. So when we're talking about speed, we're interested in the magnitude of the velocity. Now there's an easy way to tell when your particle is speeding up and when it is slowing down. Your particle speeds up if our acceleration and our velocity are in the same direction. And because I'm talking about the direction here, I should probably put my vector symbols over top of here. Okay. I'm talking about the acceleration vector and the velocity vector. So you can kind of imagine that we've got a situation where our velocity is positive, so it's pointing in the right going from left to right. Okay. Our acceleration vector is also positive. It also points from left to right. You can think of the acceleration as providing a force to this particle. So if it's traveling in this direction and the acceleration is in that same direction, it's going to speed up. It's going to slow down if our acceleration and our velocity are in opposite directions. There's an E on opposite. So same kind of picture here. We can imagine our velocity is positive. What if our acceleration is negative? Okay. If we think of the acceleration as providing a force, the force is being applied opposite to the direction of motion. So it's going to tend to slow this thing down. So even though our velocity is positive, acceleration is causing it to get smaller in magnitude. So how can we figure this out? Well, for this particular question, we know that the acceleration is always positive. Let's write this a little different. A as a function of t is always positive. Now, I should write that a little bit differently. I should say our acceleration function was a as a function of t is equal to 6t is always positive for t greater than 0. Okay? I don't want to write something like acceleration is always positive because it's not always positive. It's always positive in this particular question. So if we want to figure out where this thing is speeding up or slowing down, we have to figure out where what the sign of the velocity is for different values of t. So let's say we're interested in where this thing is speeding up. We're asking ourselves the question, where is velocity greater than 0? Or where is v as a function of t greater than 0? So how do we figure out where v at t is greater than 0? Well, we can do an interval chart, just like we did yesterday for our velocities. Our velocity function was 3t squared minus 12. First thing we should do is figure out where is our velocity 0. Because finding those points where velocity 0 is going to give us the values that we need to divide our t values into intervals. They provide the boundaries of our intervals. So we want to factor this expression. So we can common factor out the 3, and then we're left with 3t squared minus 4, which factors as a difference of squares. So our two zeros are t equals positive and negative 2. These are the positions where our particle stops. So let's set up our interval table here. We're going to have an interval from 0 to 2, and then another interval from 2 to positive infinity. No, wait, not positive infinity. The limits on t were, our function only worked between 0 and 10, so we only need to check the interval from 2 to 10. And again, what we're doing here is we're checking the sign of each of these terms in our velocity function. To figure out, overall, where is that velocity function positive and where it is negative. So that first term, 3, is always positive. T minus 3 is going to be negative, and then it is going to be positive. T plus 2 is going to be positive and positive. So our velocity function is negative from 0 to 2, and then positive from 2 to 10. Our acceleration function was positive and positive. So where's this thing going to be speeding up? Well, it's going to be speeding up in this interval here where both the velocity and acceleration have the same sign. So it is speeding up speeds up on this interval 2 to 10. And then it slows down from 0 to 2. Okay. Make sense? Malcolm?
Is it t minus 3 or t minus 2?
Oh, it's t minus 2, yes. Let's fix that. Sorry, McKenna?
I just don't know what you did after you found that it was like,
So next up, we want to sketch graphs of the velocity and the acceleration. And I've given you a graph already of the position function. This is what the graph would look like. This is position up here. This is t. This is s as a function of t over here. And even though it appears on our graph, we can kind of eliminate this little chunk down here because we said that our time only began at t equals 0. Down below it, we want to make a sketch of what our velocity looks like. Well, we know what our velocity function is. It is 3t squared minus 12. So we know that at t equals 0, it's going to be way down here at minus 12. In the previous question, we figured out where our velocity was equal to 0. It was equal to 0 at negative 2 and positive 2. So we know that it's going to cross the x-axis right there at positive 2. And I've just kind of lined that up with the 2 that I had up there. What is the shape of this graph going to be? If we look at the function, 3t squared minus 12, what kind of a curve is that going to have?
Parabola?
It's going to be a parabola, and the leading term is positive, so it's going to open up. So our velocity function is going to look something like this. Okay. Now, the important point to notice here is our velocity function right here has a 0 at t equals 2. What is our position function doing at that point? Well, at that point, our position function has got like a little turning point. You can imagine the particle, it's traveling in the negative direction, it stops, and then it turns around and it goes in the other direction. So at that point, our velocity has to be 0. So our velocity changes from negative to positive at that point where our particle turns around. Now, what about our acceleration function? Well, we know what our acceleration function is. It is 6t. What is that graph going to look like? Well, it's just going to be a straight line starting at 0 and going up. So our acceleration function is a linear function. Our velocity function is a quadratic function. Our position function is a cubic function. Okay? So each time you take a derivative, you're sort of going down one order of magnitude in your function. Okay? So from cubic to quadratic down to linear. All right, last question here. Some more graphing stuff. Okay? You've got a graph there that shows the position function of an object. So this is position as a function of t, and this is t. And we're asked a series of questions about it. At what points on the graph is the velocity 0? During which intervals is the velocity positive? During which intervals is the velocity negative? During which intervals is acceleration positive? During which intervals is acceleration negative? And our intervals, we've got these points labeled A, B, C, D, and E, so we'll use those labeled points to talk about our intervals. At what points on the graph is the velocity 0? And the key thing to think about when you're interpreting this is, what does velocity mean in terms of our graph? Okay. Velocity, or the instantaneous rate of change, is represented by what graphically? Right? The turning points will be where our velocity is 0. Okay. So what are our turning points here, Riley? B and D, right? Okay. So the other way of thinking about this, where I was kind of trying to lead you there, is that our velocity is represented by the slope of the tangent to the curve. So if I go to those points B and D and I draw our tangent to the curve, those tangent lines are horizontal. They have a slope of 0. So during which intervals is the velocity positive? So where on this graph can I draw a tangent to this curve that is going to have a positive slope? Positive slope meaning going up as we go from left to right. What do we think here? Maureen? Yeah, between A and B, I would draw something like that. So I'm just going to say A to B like this. Or maybe I should use that interval notation. A A comma B. There we go. And where else? Malcolm?
From D to E positive and negative.
Yeah. We'll just say from D to E here, and we'll ignore this little chunk over here. Right, during which intervals is the velocity going to be negative? What do we think? Radhika? From B all the way to D. Okay. Now, we could have, you might have thought we should put down B to C and then from C to D, but then what is the slope of the tangent at C? Well, it's definitely, if I go right at C, it's still a negative slope, so we want to include C in that interval there. Okay, during which intervals is the acceleration positive? Okay. There are two ways to try to think about this. One is to think about acceleration as the change in velocity. So the change in the slope of the tangent. So is our tangent getting steeper or is it getting less steep as we move from one of these points to the other? The other way to think about it is to try to just sketch what the velocity curve would look like. And sketching the velocity curve is probably easier. So let's do that. We'll just take a little bit of space down here, V at t. Okay. What is our velocity curve going to look like? Well, if we start at A, our velocity is positive. Okay. We get to B, our velocity is 0. From B down to D, our velocity is negative. At D, it is 0 again. And then at E, it is positive again. So we know that there are 2 points where it's going to be 0. Let's just put them on our graph there, and we will label them B and D. If our velocity starts off positive, it's got to start off up here, go through that 0, turn around, come back up to go through that 0, and then be positive again from D to E. So I guess we could label this A, E, and this is going to be C right down here at the bottom. Okay? If we think about this and how the slope of the tangent is changing, at point A, our slope is pretty steep. It's getting less steep, less steep, less steep, less steep, less steep, till we get to B. Okay? Then it is getting still less steep as we go from B to C. And then we get to C, it starts becoming steeper. Okay, so it gets back up to 0. And then beyond D, it gets steeper, steeper, steeper still. On our velocity graph down here, we have to think about the slope of the tangent to our velocity curve. So it's delta V, or slope of the tangent in this graph over here. So where's our acceleration positive? What do we think? Where on this little velocity graph can I draw a tangent that has a positive slope? McKenna, you raised both hands there. That was such eagerness there. Okay, Malcolm.
From C to E.
From C to E. Yeah. Okay. We draw the slope of the tangent here. Yeah, it's positive. We draw the slope of the tangent, the tangent there. It's got a positive slope. Okay. Where is the acceleration negative? Well, where's the slope of the tangent here? Going to be negative. Over here, negative, negative. So it's got to be from A to C.